session, we will be able to explain the trends of atomic properties in the periodic table and arrange elements according to periodic trends. And so there are 5 common atomic trends. First one is atomic or ionic radius. Second one is ionization energy. The third one is electron affinity. Fourth one is electron negativity. And the fifth one is metallic character. Okay, and these are our springboards towards chemical bonding. Okay, so I'd like to introduce this new concept. I understand that you were able to talk about the periodic table in junior high, right? I'd like, can you give me feedback on to what extent your discussions were? Like, were you able to talk about the periodic trends? Hello? Is it me or the net is slowing down already? Yeah. Hello?
We can hear you, sir.
All right. Sige. So, do you remember taking up the periodic trends in junior high?
Yes, sir, but I don't think we really elaborate on that topic.
Okay. Sige, sige. So for now, we'll be trying to elaborate it. Okay. I'd like to introduce this concept. Okay. I'm afraid it will be a repetition of your lessons in junior high, no? So I like to try and to provide more concepts needed. So effective nuclear charge. So in layman's term, the effective nuclear charge is just the force of attraction that an electron feels from the nucleus. Okay? Take note that the nucleus of an atom is positively charged. For example, you have sodium. Okay? Sodium has 11 protons. Its atomic number is 11 if you try to look at your periodic table. Now, sodium Na has one valence electron, which is in the 3s orbital. So 1s2, 2s2, 2p6, 3s1. And that is this one electron here. Below below that valence electron for sodium are 10, okay? 10 electrons, so 10 core electrons. So when you talk of nuclear charges, it is just the charge or the amount of attraction that this valence electron feels. Okay? So in here, the charge that the electron feels, the effective nuclear charge. And why is this important? Take note that negative particles are attracted to positive particles. Okay? So, meaning to say, if wala ni siyang electron cloud, then we expect this electron, this valence electron, to really get attracted to the nucleus. However, that doesn't happen because there are electrons at specific energy levels, okay, that are shielding, okay, in a way shielding this valence electron. So meaning to say the pull of the pull of the nucleus on the blue electron here is lesser, okay, it becomes lesser because the orange electron cloud here, that those 10 electrons are kind of protecting this valence electron. Okay, so that's why we have this combined effect. Okay, so instead of experiencing a pull of which has a value of plus 11, okay, we subtract 10 from it, so the nuclear charge is plus 1. Okay, and then that has an effect on the atomic size of sodium, which we will see later on. All right. So mathematically, we can represent the effective nuclear charge of sodium that way. So ZF Okay, ZEF is equal to Z minus S, where Z is the atomic number. As for this case, it is 11, and S is the screening constant. The screening constant is actually then is approximately close to the number of inner electrons. So as for this case, we were saying that sodium has one valence electron, so the other 10 must be the inner or the core electrons. So we can substitute 10 as our S. All right. So the effective nuclear charge of sodium is actually 11 minus 10, that is 1, okay, or positive 1. All right. So that means na diminish instead of positive 11 being experienced by the electron is only positive 1. Okay. And since the charge experienced by this electron is only positive 1, that means hinay lang siya is kind of weak. So that makes this electron easily removable. Okay, it's far away from the nucleus and it is easily removable. All right. So that's the significance of the effective nuclear charge. So, for example, which element's outer shell or valence electrons is predicted to have the largest effective nuclear charge? Is it oxygen, nitrogen, chlorine, or calcium? So, how do we do this? First is we have to know how many electrons there are for oxygen, diba? So oxygen has 8 electrons, a neutral one, and then this is 1s2, 2s2, 2p, 4. All right, 1s2, 2s2, 2p4. And so therefore, the valence shell of oxygen has 6 electrons. Okay, so if you draw the schematic diagram of oxygen, that is 8 plus, and then this is the first orbital. This is n is equal to 1. So how many electrons are there for n is equal to 1? There are 2 electrons. All right. And on the second energy level, there are 6. Okay, 2 plus 4. Okay, just look at the coefficients. And then there are 6 valence electrons: 1, 2, 3, 4, 5, and 6. And so we are asked, what is the nuclear charge, effective nuclear charge experienced by the outermost electrons? So what we can do is just find ZEF is equal to the atomic number minus the screening constant. And when you talk about the screening constant, these are our inner number of inner electrons or core electrons. Okay, either way you can call them core or inner electrons. So this one is 8 minus 6. Oh, no. 8 minus inner man is 2. Okay, 8 minus 2. So you'll have 6, positive 6. Okay, so compared to sodium a while ago, remember that the effective nuclear charge of sodium is plus 1. And then now we have oxygen as plus 6. So that means the outermost electrons of oxygen experience a greater pull, okay, than the outermost electron of sodium. All right, and this affects the atomic radius because the greater the pull of the nucleus on the electron cloud, okay, the higher this value, the smaller, okay, the smaller your atomic radius will be. So higher ZEF, smaller radius. Okay, the smaller your atom will be, and the more difficult it will be to remove a valence electron. All right. So here are the answers for the rest of the items. So oxygen, you have 6. Nitrogen, you have 5. Okay. Uh, Chlorine, you have 7. And calcium, you have 2. Okay. So how do you interpret these results? Uh, the effective nuclear charge is the charge experienced by an atom, by an electron at the outermost level. All right. So the higher the value for your Zeph, okay, the stronger their attraction. And then the tendency is it will draw the electron cloud nearer to the nucleus, and that means you will have a uh, smaller atom, smaller radius for the atom. All right, question?
Hello, sir.
Yes.
So does if the strongest relates to the atomic radius, does that mean francium is the atom largest element with the atomic radius in terms of atomic radius?
Yes, yes, very good. Okay, so
Uh,
that's actually where I am leading to. Okay, so in terms of atomic radius, okay, so we're correct, Enoch. Francium is considered to be the largest element. Okay, and it's the largest element. It's the one with the biggest or the largest atomic radius, but it also has the least energy to pull out its valence electron. Okay, remember there are quite a number of atomic properties. So you have atomic radius. The next one is ionization energy. Ionization energy is the energy required to remove an electron. So when you talk about francium, since its valence electron is very far away from the nucleus, okay, and the effective nuclear charge is very small, okay, plus one lang, then it would be easy to remove the electron from francium. Okay, so lesser and it will have the least ionization energy. Okay, but it will be developed as we go on. All right, so
thank you, sir.
thank you for that, Enoch. Let me continue for the definitions now and the trends for atomic radius. This one, we already discussed this. Okay, it's one with the highest coefficient. So we'll skip this part. Okay, so we go to the first atomic property, okay? Let me talk about atomic radius and ionic radius because it will affect all the rest, okay? How hungry the atom will be for more electrons, or how much energy will be expended once the electrons will be incorporated inside the atom. So some things like that. Okay, so when you talk of atomic radius, it's half the distance between the nuclei of two bonded atoms. Okay, this definition works for non-metals. Okay, those that are existing as diatomic molecules, meaning, for example, O2. Diba? O2 is made up of two oxygen atoms bonded together. All right? So in the atomic radius is basically half the distance between their nuclei. Okay? But for metals which exist as monoatomic elements, it's just the distance from the nucleus to the electron cloud, to the outermost edge of the electron cloud. All right. So, however, this is very difficult to determine because the electron cloud is um, it's very hard to determine their boundaries. Okay, so the more formal definition will have to be the one in the nonmetals. Cannot say yeah. All right. So atomic radii are usually measured in picometers or angstroms. Okay, so pico, that's times 10 to the negative 12, or an angstrom is times 10 to the negative 10 meters. Here, for example, two bromine atoms bonded together are 2.86 angstroms apart, So the radius is half that one. So 2.86 divided by 2, you have 1.43 angstroms. So the A not here, A with a circle on top is our angstrom. All right. So the trend for, it says here the trend for atomic radius in a vertical column is to go from smaller at the top to larger at the bottom of the family. Can anyone tell me why this is? Why do you think? Okay, if you try to look at your periodic table, I hope you have them now. The atomic size or the atomic radius, they can be interchanged. Huh? They can be, the terms can be interchanged. The atomic radius increases from top to bottom for, of the period of the family or for each group. And my question is why?
Hello, sir.
Yes.
I think I can relate that with the largest energy that you have discussed a while ago.
All right.
Because since, let's say, for example, helium, it has the smallest atomic radius because it it doesn't have a closer shell inside of it, so it's like two, and then it's closely attracted to its nucleus, so it has the smallest radius. However, for francium, since it has only one plus one, only one valence and electron, so it has the it has the lowest energy that it gets attracted to, so it has the largest atomic radius, I think.
Yes, very good. So in terms of the effective nuclear charge, okay, the it becomes the francium has a small, very small effective nuclear charge, and so that's why its outermost electron is far, very, very far away from its nucleus. Okay, it's also important to note. Thank you for very much for that, Enoch. It's very important to note also that as we go through the from top to bottom, there are additional energy levels. So there are additional electrons which can shield, okay, which can shield the valence electron, and there are additional energy levels. All right. Now, a question about from the vertical trend rather. Okay. So as you go from lithium to sodium to potassium to rubidium, there is an additional energy level. Okay, and when there are additional energy levels, uh, the pull of there are more electrons that can shield the valence electron. There are more core electrons that can shield the valence electron. Okay, and so that's why the pull of the nucleus becomes lesser as well. Now, the trend across a horizontal period is less obvious. So what do you think happens to the atomic structure from left to right? Okay, the trend is from, from left to right of the periodic table for each row, there will be additional protons to the nucleus. Okay, there will be additional protons and additional electrons in the electron cloud. So if that happens, there will be a greater attraction between the positively charged nucleus and the negatively charged electron cloud. All right, and if that happens, the electron cloud is drawn nearer. Okay, so the increased attraction pulls the electron cloud in, making the atom smaller as we move from left to right across across a period. All right, so the trend for increasing helium is the smallest, as what Enoch has mentioned. So this is one of the exceptions for the trend. Okay, take note that in chemistry there are a lot of trends, but there are also a lot of exceptions. Right? So the trend here is that way for increasing. Okay, when you talk of increasing atomic sizes, The smallest is helium. The largest one will be francium. And if you are asked to arrange, you will, according to increasing order, you will just have to look at the periodic table from right to left, down, right to left, then start right away from the right to left, going down. All right, so there will be a sample exercise later. Okay, that is for atomic radius. Are there questions for clarification? Now, let me talk about the sizes of ions. So we have this picture. I would like you to note any significant observations and share it to the class. So for the pink spheres, these are your ionic forms of your metals. The gray ones are your neutral elements. Okay, the gray part of the sphere are your neutral elements, and then the pink ones are your cations, the blue ones are your anions. I would like you to compare the sizes or the atomic radii of the cations or anions compared to their neutral counterparts. What have you observed? What do you observe? Anyone? Or let's emphasize uh, a few examples. So you have here sodium and chlorine. So the atomic radius for the neutral sodium is 1.54 angstroms. However, for the sodium ion, it is 1.16 angstrom. Okay, the same thing for calcium. I'd like you to notice the trend. For a neutral calcium atom, it's 1.74 angstrom. For the cationic calcium or the calcium ion, it's just 1.11. In here, we have the nonmetals, chlorine and sulfur. So for chlorine, the neutral atom for chlorine is 0.99. And then the ionic form of chlorine, the chloride ion, is 1.67. So from 0.99 to 1.67. For sulfur, for neutral sulfur, that's 1.02, and the ionic form is 1.70. Any observations between neutral atoms and their cationic or anionic counterparts?
Hello, sir.
Oh, sorry. You go
It's
ahead.
okay.
Sorry.
No, you can. I was
Oh,
actually gonna mention you, but yeah.
oh,
He
thank.
actually said something. But actually, cations shrink as the electrons goes out, and then anions expands the radius as it electrons gets added. That's my observation, sir.
Okay, that's good. Who was the other one? Thank you for that, Enoch. Here we have from John Ver, fewer electrons, atomic radius henceforth shrinks. Okay, and ions reverse because more electrons are added into the atom. Okay, that's very good. So both are correct. Okay, so between a neutral atom and a cation, take note that when you talk of cations, uh, one or two or three electrons have been removed from the electron cloud. All right. So once you remove an electron from the electron cloud, okay, the repulsions between the electrons will lessen, and the electron cloud will, the pull of the nucleus will become much stronger. Kaya di naman sila balance, mas daghan man ang protons kaysa sa electrons. So that means the nucleus pulls in the electron cloud more. Okay, making the size of the metal shrink. as what has been mentioned by Enoch and Janver. Now, in terms of the ionic radius, anionic radius, okay, when you say anion, it has more electrons, diba? So, for example, chlorine has one additional electron. For sulfur, it has two additional electrons. So what happens here is, as what has been mentioned, when you add more electrons, you will increase the repulsion in the electron cloud. And once that happens, if there are increased repulsions in the electron cloud, then they will try as much as possible to stay away from each other, okay, making the radius a little bit bigger for the ion. All right, so meaning cations are smaller than their neutral counterparts, anions are greater than their neutral counterparts. Okay, and why is this relevant? Why is this important? For example, there are certain ions in the body which are received by receptors. Okay, so when you talk about biology, there are a lot of hormones, there are a lot of mechanisms that involve ions. That's why you have sodium, or you can also have potassium to facilitate nerve impulses. Okay, those metals there exist as ions, Na plus or K plus. Okay, the operations of the muscle, and they can only be absorbed by the receptor if they are following the certain size or atomic radius. Okay, so the body has certain receptors that will only absorb specific ions with their corresponding sizes. Okay, yeah. We will now discuss the trend, but anyways, it will be clearer in the video. So the next few discussions are on ionization energy, electron affinity, and electron negativity. All right. So I'd like to ask the help of a good friend of mine, Joe. This is a video bit. Professor Dave, to explain to us the different atomic properties and their trends in the periodic table as well. All right. So here.
Let's talk about the periodic table. He knows a lot about the science stuff. Professor Dave explains.
Can you guys hear clearly?
Yes, sir.
Sure.
Okay,
Yes, sir.
Sure.
Sige, let's continue.
Pretty much everyone knows what this is, even if they don't know much about chemistry. It's the periodic table of the elements, which at first seems like a random arrangement of substances, most of which sound strange and foreign. But the way the elements are arranged reveals many beautiful patterns that tell us about how nature operates. In the mid-1800s, lots of chemists were trying to come up with a way to depict all the elements in table form, and many different formats were proposed. But it was the one by Dmitry Mendeleev that stuck, because of how well it correlates data as well as its predictive powers. He arranged the elements into rows called periods and columns called groups. Elements that had similar behavior were put in groups together, which helped to correlate existing data. And it also predicted the existence of elements that had never been seen before. With the gaps in the table, Mendeleev said there must be elements that go in these spots, and he predicted some of their properties. Eventually, these elements were discovered with the properties precisely as expected, and now we have all the metals, metalloids, and non-metals organized nicely. It wasn't known at the time, but the reason elements in the same group behave similarly is because they have the same number of valence electrons. Look at group 1, for example. These elements all have one valence electron, or one electron in their outermost shell. As you go down the table and n increases, you gain a shell each time, but whichever is the outermost shell, there is only one electron in it. Every element in group 2 has 2 electrons in its outermost shell, and so forth. This simple fact determines many characteristics about each element in ways we will continue to see as we learn more chemistry. There are some periodic trends that we can recognize when we look at the table. The first one is atomic radius, or the size of the atom. As we proceed downwards on the table, atomic size increases because we add shells. As we go to the right, atomic radius decreases because we are moving within a shell, and each element to the right has one more proton in the nucleus than the last. So there is a stronger electromagnetic attraction felt by the electrons, and the radius shrinks. That means overall, atomic radius increases going this way on the periodic table. Ionic radius is a little different. Electrons repel each other, so adding an electron makes an atom bigger. Taking one away makes it smaller. Ions with the same electron configuration will have their radii decrease as the atomic number increases. Next.
Okay, do you catch that?
Ions as the atomic number.
Okay, so remember we were talking about the isoelectronic series. Okay, so this is an isoelectronic series. These are species that have the same number of electrons. So O2, F minus, and E, but they have different number of protons. So you might have noticed that in an isoelectronic series, as the atomic number increases, then the size decreases. So bali siya. So the more protons you have, the more attracted the electron cloud will be. Okay, especially if it's an ion. So for an isoelectronic series, the trend is decreasing if you have an increasing atomic number. All right. Question? And so, okay, next.
Increases. Next, we look at ionization energy. This is the energy required to remove an electron from the atom. It will always be an electron in the outermost shell. The electromagnetic force that attracts the electrons to the protons drops off very quickly with distance. So the farther away an electron is from the nucleus, the easier it is to pull it away. This means the ionization energy trend is precisely the opposite of the atomic radius trend. Francium, a very large atom with only one valence electron, will be easy to ionize because the electron is so far away from the nucleus, and atoms like to have their outermost shell completely full. Losing the electron means this shell is gone and the one below is completely full, so elements in group 1 will easily lose one electron. Looking at the opposite corner with helium, there is only one shell, so the electrons are very close to the nucleus, and the shell is full, so it is very stable. For this reason, it requires much more energy to ionize helium. So the ionization energy increases going this way on the periodic table. Elements can have successive ionization energies for removing more than one electron.
All right. So this table shows us the amount of energy required to remove the electrons. So we call them ionization energies. Okay. Now in here, for example, for sodium, the sodium has one valence electron. Okay. So its first ionization energy is given by this value. Okay. Now for magnesium, magnesium has two valence electrons. If you look at your periodic table, it belongs to group 2A. All right. So the energy required to remove the first electron is 738. The energy required to remove the second electron is 1,451. All right. Now aluminum has three valence electrons, and you can see here the ionization energies for each of those valence electrons. I'd like you to notice something. Look at the gap between the border lines between the beige or the orange and the sky blue values. So from 496, it suddenly became 4,562. That's for sodium. For magnesium, from 1,000, the second ionization energy is 1,451 kilojoules per mole. It suddenly became 7,733. Okay, so there's if you've noticed, there are very big jumps in ionization energy. And why do you think that happens? Anyone?
Hello, sir.
Yes?
I think it is because those at the leftmost sides, like isoelectronic series, like the noble gases, like following the octet rule, the noble gases has the stable state, has the most stable states among the all other elements. If we compare it, then if we try to get them out to their stable state, it requires more energy to, yeah, give off in order for the electrons to get out or be released,
To be removed.
to
Okay,
be
very
removed.
yes, very good, very good. So if you've noticed, the starting values for the blue ones, these are actually already in their ionic form, okay, and they have followed the configuration of the noble gases already. So for example, as if you remove one electron from sodium, it will already have the electronic configuration of neon, okay, which has 8 valence electrons. And as what Enoch was mentioning a while ago, 8 valence electrons that makes the atom very stable, okay, that such that it will require much more energy to remove any one of those 8 electrons. Okay, so that's it. These are now the configurations of the noble gases. So that's why there is a very big jump, because you are actually trying to remove an electron which is actually in the stable state already for the atom. Okay, do we have questions? So the another pattern here is the more electrons you would like to remove, the more energy will be required, because as you know, the lesser the electrons are in the electron cloud, the more attracted the electron cloud becomes to the nucleus, and making it harder to remove, requiring much greater energy to remove those electrons. Okay, so continuing.
A second ionization energy will always be greater than the first and continue to increase from there, since the more electrons you remove, the less stable the atom becomes. An element will have a huge jump in ionization energy after you take the last one in a shell, because then you jump to the noble gas electron configuration from the previous shell, which is full, so it really won't want to give up any more electrons. There are just a couple exceptions to the ionization energy trend, but we can rationalize them. Look, for example, at the second row. From lithium to neon, the ionization energy should increase each time we add a proton to the nucleus and the radius contracts a little. But something like oxygen, which dips downwards from nitrogen's ionization energy, does so because of orbital symmetry. Here is nitrogen's orbital diagram, as well as oxygen's. Notice that nitrogen's 2p orbitals are precisely half full. This gives nitrogen a special stability, just like elements that have a full outermost shell. If nitrogen loses an electron, it loses that special stability. But if oxygen loses an electron, it will gain that special stability. That's why oxygen's ionization energy is a little bit lower than nitrogen's, even though oxygen has one additional proton. All deviations from the ionization energy trend can be explained by discrepancies in orbital symmetry, like this one. Next.
All right, so this is quite similar to the exceptions that we have in electron configuration, no? The anomalous electron configuration. So the key idea here is the atom becomes more stable if it has a half-filled shell or a full shell. All right, and so if it is more stable, then it will be harder to get the electrons. Okay, that explains the discrepancy in the trend. All right.
Deviations from the ionization energy trend can be explained by discrepancies in orbital symmetry, like this one. Next, we will look at electron affinity. This is exactly the opposite of ionization energy, since ionization energy is how much energy you need to remove an electron, and electron affinity tells us how much an atom wants to gain an electron. Disregarding the noble gases, as their shells are full, electron affinity increases this way. Fluorine has the highest electron affinity because if it gains one electron, it will have a full shell, or a noble gas electron configuration. Looking at the opposite corner, these elements don't want to gain electrons. They would rather lose them. Exceptions to this trend happen for exactly the same reasons as the exceptions to the ionization energy trend.
Okay, so when you talk about electron affinity, that affinity means being attracted to, no? So, for example, girls have an affinity for what kind of things? What puppies or flowers, something like that. So when you say electron affinity, it's just like an attraction to electrons. But by definition, that is actually the energy that is released once an electron is incorporated into the electron cloud. Okay, so it is the energy released once an electron is incorporated or is added to the electron cloud. Okay, so to accommodate, to make the atom stable once more upon the entry of the new electron, it has to release some of its energy. Okay, and that energy is what we call electron affinity. Okay, and the trend is.
Lastly, we want to look at electric reasons as the exceptions to.
So the trend here is opposite. So you exclude the noble gases because they're practically stable. They don't want to have electrons anymore. So for electron affinity, it increases from left to right, then bottom to top. Okay, so from francium to here, LV, then going up, cesium towards astatine, okay, going up, rubidium to tellurium, such that you will have fluorine as the highest, which has the highest electron affinity. Okay.
Ionization energy trend. Lastly, we want to look at electronegativity. This is the ability of an atom to hold electrons tightly. It will increase this way because a smaller atom like fluorine with more protons for its energy level, or a higher effective nuclear charge, will hold electrons best. Again, we will disregard the noble gases for this trend. Electronegativity will be important in the next clip where we learn about chemical bonds. So the trends to remember are atomic radius, which goes this way, as well as ionization energy, electron affinity, and electronegativity, which all go this way. Let's check comprehension.
Okay, so we will be discussing more on electron affinity and electronegativity once we have chemical bonding already, because these atomic properties really have an effect on whether the bond will be polar or non-polar. And then after that one, whether the molecule will be polar or non-polar. All right, so we'll reserve that for further discussions. Now, let's end this synchronous activity by answering this uh, exercise. Okay, list the atoms in order of increasing atomic radius. So you have silicon, krypton, chlorine, potassium, and calcium. So you can just sound off whichever you want to answer. And this will be our checkpoint for this discussion. Sige. How many minutes do you need? Anyone? So if you try to look at your periodic table, you can just highlight your elements. So try to look for silicon, Si, krypton, and chlorine. potassium also, okay, and calcium. So the trend in the periodic table is that it increases, atomic radius increases from right to left, going down, top to bottom. So from right to left, so that means our smallest atom, okay, the smallest atom is chlorine, Cl, okay? Then after chlorine is silicon, okay, from right to left man. So that's chlorine, silicon. After silicon, you have krypton. After krypton, you have calcium and then potassium. All right. And then which one is the larger atom? Let's just check between Br and Br minus. So as we said, anions have greater atomic radii than their neutral counterparts. So for this first item, we choose Br minus. All right. This one, Cl and Ar. So this belongs to an isoelectronic series. So the one with the bigger atomic radius is your Cl minus, okay? Because as we said, uh, increasing atomic number for an isoelectronic series, increasing atomic number means the radius becomes smaller. Okay, so as for this case, uh, chlorine comes before argon, okay? So that means the chlorine ion, Cl minus, must have a greater atomic radius. And then between K and K plus, of course, we know that it's just the reverse of the nonmetals. So the neutral atom potassium K is larger than K plus. Okay? So here are the answers. Right. Are you still with me or you're taking your lunch now? Here we have an answered A. So, thank you very much, Enoch and Prince, for keeping me company. Okay, so that's it. Those are for atomic properties and periodic trends. Tomorrow, we will be having some laboratory activities. Okay, so labs 2 and 3. This is regarding the quantum mechanical model so that you can also review for the test on Wednesday. Quantum mechanical model and build your own periodic table. So the trends are also there. All right. So asynchronous tomorrow, no need to log in. Okay, no need to log into the meeting. And then the 20 item tests on Wednesday. Okay, just very short. Okay, so if there are no more questions or clarifications, that would be all for